Have you ever stopped to think about how many things in life just move in circles? I mean, think about it. The seasons, the days of the week, the hands on a clock. Well, it turns out there's a really cool mathematical concept that describes this whole idea perfectly. And today, we're going to unpack it using just one single page from a textbook.
So let's start with a really simple question. From the 4 seasons to the hours in a day, our lives are just full of these cycles, right? We're constantly on these little journeys that eventually bring us right back to our starting point. But have you ever wondered, how do you actually measure the length of one of those journeys?
Okay, let's make this super simple. Think about a clock. Let's say you start at 12 and you decide to jump forward 3 hours at a time. Your first jump lands you at 3, then 6, then 9, and one more jump, and bam, you're back at 12. It took you exactly 4 steps. That number, 4, that's the length of the cycle. And that is the absolute key to understanding this whole thing.
Now, this whole idea of steps to get back to the start, it's way more than just a little party trick with a clock. It's actually a fundamental concept in abstract algebra. It's got a formal name, a precise definition, and it is the key to unlocking the hidden structure of all kinds of complex systems. So, you ready to dive in? This right here, this is our source material for today. Now, I know it might look a little intense, but trust me, by the time we're done here, you'll see it's really just a more formal, kind of fancy way of talking about our clock analogy. So let's break it down, piece by piece.
The order of an element. That's it. That's the official name for what we've been talking about. It's just the answer to our original question. How many steps does it take? That's all it is. And it's the key to describing these repeating patterns.
Okay, so you see this phrase in the textbook. It might look like a jumble of letters, but it's actually super simple. N is just our number of steps. A is the action we're repeating, like add 3 hours. And E is our starting point, our 12 o'clock. So the whole equation is just a very compact way of asking, how many times do I have to do A to get back to E?
This brings up a really interesting question, though. What if a cycle never actually repeats? I mean, what if you have a process that just keeps going and going and going forever without ever looping back to where you started?
Well, the textbook has an answer for that too. An element can have a finite order, which means it repeats, or it can have an infinite order, meaning it just goes on forever. You can think of it like the difference between a round-trip flight and a one-way ticket to somewhere you've never been.
Okay, this is where it all clicks together. Look how perfectly these abstract symbols from the text map onto our simple clock analogy. A is our action, add 3 hours. E is our starting point, 12 o'clock. And N, the order, is the number of steps it took us, which we figured out was 4. So that formal notation you see, O action A, that's just shorthand for the order of adding 3 hours. See? Not so scary.
So now that we've got the basic idea down, let's look at a little wrinkle. Mathematicians sometimes use a different shorthand for the exact same concept. It's kind of like using different languages to say the exact same thing.
So, there are 2 main ways they write this down, multiplicative notation and additive notation. We've kind of been using the multiplicative one so far, a to the power of n. But the additive one, n times a, is actually perfect for our clock example. Think about it. 4 times adding 3 hours got us back to our starting point. It's the same idea, just written down with different symbols.
All right, let's shift our focus for a second to the starting point itself, or what the textbook calls the identity element. This is sort of the anchor of our whole cycle. And it has one very, very simple rule that makes it unique.
The order of the identity element is always, and I mean always, 1. No exceptions, period.
And the logic behind this is beautiful in its simplicity. If you're already at the starting point, how many steps does it take to get back to the starting point? Well, just 1. You don't have to do anything. You're already there. It's the shortest possible cycle.
So, let's just quickly recap what we figured out. We've learned that this fancy term, order of an element, is really just about counting the length of a repeating cycle. We've seen that these cycles can either be finite, they loop back, or infinite. And we've learned that the starting point itself always has a special order of 1. It seems like a simple concept, but it's an incredibly powerful tool for understanding the hidden structures all around us.
We started with a simple clock, but this idea of the order of an element applies to so many things, from modern cryptography to the way molecules behave in chemistry. Once you start looking for these repeating patterns, you will see them absolutely everywhere. It's like this hidden rhythm that defines the world. So my question for you is, what will you see differently now?